Imperial College, where he's doing a postdoc for the last 2 years. With us here in the theory seminar, Donal did his PhD at University College Dublin some years ago. Then he worked for some companies, and he went back to academia, did a postdoc the last 2 years at Imperial, if I got it wrong. If I got it right, sorry. So he has been working on social media research, and he's also been working on some projects where it's also part of his working within these projects that the visual analytics group here has or had together with Imperial College and Aalto University. And today he's going to talk about contemporary applications of social media research. And please.
Okay, thanks, Panos. So just before I start, I might have pitched this at the wrong level because some of these slides have kind of come from lecture notes from undergrads. And I think, given the group here, we might be able to skip over some of them, just kind of initial introduction to some network ideas and things that we need when we're looking at analysing social networks. So if I'm going too fast, you can ask me to slow down. If you want me to dive deeper into something, just shout out and ask.
Is there kind of marker there where you can write things there?
Yeah, I think there's a marker here on the board. So if
if you want to do something more detailed, then you can.
Yeah, I think there are 2 or 3 things that I'll probably go into a little bit more depth than I have on the slides on the board. Right, so that's the intro, and maybe just from the title, so social media research. We're going to start talking about social networks, and then I guess I kind of view social media as being the network and the data that you get with the post stream of messages. So that's 2 of those things combined. I'm going to look at 2 examples of that. So we've got one of the research projects we did was more about the network itself, the actual connections between people, and then the second one was kind of not using that information at all really. It was just using the post that people put up and information that you can get from that. So I guess that's terminology-wise. I said that social media is, I guess, the network and the stream of posts that you get, say, from Twitter or something like that. So, just as a starter, I need to give you kind of a quick example of what you can do with quite straightforward algorithms and presentation on social networks. So this is a friendship network from Facebook, and it's my own one, and we've got here the different communities coloured and by whatever the partition class is for the communities. So you can load your data into something like Gephi, which is a tool for network analysis. You can run community detection algorithms on it, and you get here things that you can then colour by those communities. So with kind of off-the-shelf tools, you can get into some pretty basic but meaningful network analysis for social networks. So I've got like school friends and college friends and work friends, and you can see how they're related. And some of them, the guys that I did my PhD with, don't know any of them. One within what we call the giant component of the graph. So it's quite interesting how you can get these things out, and that either visually or through the numbers that they can tell us something about the social network that's not immediately apparent when you were just looking at Facebook or Twitter messages or posts or something like that.
What is the size, the radius of the circle? What does it represent?
Oh, that's I think it's the degree of the node.
The degree of the node. Okay.
Yeah. So it's
okay.
the smaller ones have less edges.
Okay.
Okay, so I'm probably going to go very, very quickly through this first part, and then the second bit is just a really brief idea of some of the applications. So I was thinking for this talk that we might get what are the kind of applications that people are using this stuff for, and then maybe focus in on 2 very different examples that we've worked on in ISST and Imperial for the second part of the talk. So again, I don't even know if it's worth going through this. Like, what's a network? It's composed of nodes and edges, or vertices, and you can have directed ones and undirected. And sometimes you want to put an edge weight on there in between the nodes, and that can give you some idea of the strength of the relationship between 2 different nodes. So this one is kind of interesting, I guess, because you could think what are the classic online social networks? You've got Facebook, Google+, Twitter, and LinkedIn, and then I guess from kind of social network research you can get a lot of other different things that are networks, emails within an organization, people posting things on Stack Overflow or some sort of forum like that. You can extract a network out of that, and you can analyze that then. You can get project contributors to open source projects or anything like that. One of the interesting ones in the research is who did the Dolphin Association Network in Delphi Sound in New Zealand. So there's just lots of, and there's food ingredient networks from Adamic. There's lots of different types of networks. So the food ingredient network isn't a social network, but the Dolphin one is, even if it's Dolphin. So just the idea is that I guess everybody can think of Facebook, Twitter, Google, or whatever. Those are the social networks, but there's lots more than that. Anything with people interacting together really can form these networks. So for an idea of that, we've got this image here, which you probably can't see too towards the back there anyway, but even on my screen it's pretty small. But this is the Game of Thrones characters, and the edges. So you've got actual factions of the Starks and the Lannisters over here somewhere, and then the edges between them are who's killed who and things like that. So, and the size of the edge, the size of the node is how many people you've killed. I think. No, it's how often you've appeared, and then the edges are who's killed who. So, yeah, it's a pretty fun example that somebody did by reading through all those books and creating that network. And it's another example of how to visualizing something like that with the edge trends, the coloring, and things like that. You just let your kind of human pattern matching take over to see things that you would immediately be apparent. Right, again, some more kind of basic stuff, I guess. The degree is obviously one of the most important things, the topology. And more interesting is the different degree distributions that these networks can have. Particularly in the internet, social networks, things like that. We see scale-free networks that have a power law distribution, and that's important. Getting the exponent of the power law and finding things that you have these theoretical networks and how they match up with the actual observed networks that you've collected. And you can see that if you're when you start off analyzing some sort of empirical network that you've collected, you compare it to these theoretical ones, and you see how far they deviate, and if say clustering coefficient or any of these metrics that you have about the graph are sufficiently different from your random networks. So I'm not trying to give too much of an overview on network theory here, so maybe just keep moving on pretty quickly through this one. So again, one of the other ideas, and I touched on the giant component there in that example from the Facebook thing. You've got components that are substructures, I guess, within graphs, or within networks. So see, you've got various different connected components here, and then with either being weighted or when the edges are directed or not, you can get weakly connected components or strongly connected ones. And this is the big one, I guess, for the kind of social media research. We're always generally interested in the giant component and those things that are part of it, and maybe those that aren't part of it. And as it says there, it always retains like a finite fraction of the nodes within the network, no matter how large you get. Okay, so I guess that's probably, yeah. So centrality is a little bit more important than the stuff that we'll be talking later on. So you've got in degree, we might have explained earlier on, I might have skipped past it actually. So in degree is the edges going into a node, out degree is those coming out and pointing away from a node. If you think of Twitter, somebody with a large follower count has a high in degree. Somebody who's following a lot of people, which isn't necessarily very informative. If you follow 1,000 people, do I really read a lot of what they say? Because you get this kind of stream of information that's too big for you to cognitively process. But somebody has 5 million followers or an in degree of 5 million, that's pretty informative as to their popularity within the network. So those are the two basic degree-based centralities. Then you've got betweenness and closeness. I think betweenness is can be an important one in certain networks. So with betweenness centrality, you might have two different communities, and you have things called brokers between the communities or different areas of the network. And betweenness centrality makes it, if you were to rank these people by betweenness centrality, the brokers within the network become the most important people. If you think in an organization or a company or something, you've got two departments. Anybody that acts as a bridge or links between those two departments becomes more important because of that role. If you were to model that thing as a network, you might be able to see that they have a high betweenness centrality. And then lastly, the one which you're probably all familiar with anyway, is page ranking, how that's used to rank pages on the web. In our work, we use it to rank people as being important within a network, because those people who are connected to highly followed individuals are all, get a kind of a portion of their importance. So if, you know, I don't know, Britney Spears or Justin Bieber or somebody follows you, and you only have that one person as your follower, well, they've got 50 million followers. That's pretty important. So when you say something, and if it goes through, you get a much bigger audience from that. So I think the essence for the page rank here that's important to us is this node person here that gets a lot of the importance just from the fact that how important this person is. So I guess that's the important thing with page rank. So that isn't captured in any of the other types of centrality measure. Okay. So yeah, I think we've talked quickly about communities. I'm going to slow down and go in a little bit more into depth on other things, particularly the work that we've done. So I'm just kind of give a skim over of these things. So one of the things that we look for is communities within these networks. And there's various different methods of detecting communities. You get cliques, hierarchical clustering, we've got modularity is probably the most popular one. And then, so once you've determined what are these communities from these various different methods, you get other problems. Resolution means you've got possibly overlapping communities. So depending on the scale you pick, you might see that, I'll give a real world example here, that you've got all the lecturers within a certain group, and they might form a community. If you go up larger again, they've got computer science lecturers, and that's a group, and so on, maybe up to engineering or sciences. So there's different scales, and that's important when you're looking at communities, because if you don't know the scale beforehand, it gives you all sorts of difficulties. But that's the idea. I guess I was just kind of motivating those terms. I wasn't sure how many people would have heard of them before. So we'll talk about them a little bit now. So some of the current applications. Two that I'm going to talk about today are actually only one of them is on this slide, but it's classifying individuals as influential within communities on Twitter. So that's work that myself and colleagues in the ISST have been doing. We've also been looking at identifying missing links. So we started looking at people who were being influential in networks because we were solving another problem. We were trying to get the missing edges. So it was an edge detection problem in networks, and we were looking at Twitter. The thing is with Twitter that you've got two different types of relationship going on. You've got this producer-consumer type of relationship with people who broadcast and got a large amount of followers. They're telling you information, and then you're consuming that because that's what you're interested in. Football, programming, computer science, you have an interest in something that people are influential within that sphere, and you want to consume the information of them. And then you also have the kind of assortative, homophily-based relationships, which is people that you went to school with, friends, people that you worked with together. So there's two different relationship dynamics in something like Twitter. So we wanted to understand the second one, that kind of shared likes, people who've been to school together and stuff, that kind of well understood in the literature. People who've done studies on Facebook and LinkedIn data, but the first, that influence type relationship, wasn't as well studied, so that's why we kind of got to the influence via the missing links problem. So digital marketing strategies. So obviously there's huge push now for advertising and marketing and things like that to get in and capitalize on all this information that's available in social media. And you know, they're just starting to kind of get to ideas as to how you might do that. So Panos is kind of introducing me there, and that's actually kind of my next role will be moving on to something within that social media advertising space. So I think there's a lot of kind of interesting stuff to happen in that domain, and a lot of it, I guess, is non-obvious. So if you think about somebody maybe suggesting something within a tweet, if you get to influential people and you say, you know, product placement or something like that, that might be obvious use of social networks. That you get somebody to retweet about your product, oh, isn't this great? I enjoy going to Nando's or McDonald's or something like that. That's kind of an obvious use of almost traditional marketing within this space. But there's things that people are looking at now, which is a little bit more complex, where you're like, maybe find me a community around a certain topic of interest. I'll give an example again, maybe Arsenal Football Club or Manchester United. Find me a community online on the social networks and see what they're talking about. And you kind of can't do that really through traditional methods. It's a lot more difficult, so you have to go surveying people and asking them things like that. So that's kind of use of social media for advertising. Also, yeah, detection of communities. You've got the Dolphin social network, where they found that, you know, dolphins like actually, which wasn't too surprising, but they were represented in a network way, and it's a really interesting paper. Lusso, Newman, and a couple of others, I'm not sure, but yeah, what they found is that that network was assortative, and the dolphins like spending time together by age and by sex. So, and then they found that there was some key brokers within that network. So I guess it's not something that you would have traditionally thought of capturing as a social network.
So do dolphins also use Twitter?
Yeah.
How's the data coming?
Just a Miami football team.
Yeah, so that's the painstaking observation. Was that one? That was like 2004 or something. So too early for dolphins to be using Twitter. Right. So I guess this is the main part of the talk. This is where I'm going to talk about the two projects that we've been working on last. The first one uses mostly network data. We do use some of the actual posts and streams from people as well. And then the second one is kind of different. I can't give it its proper name here because it's for a stakeholder. I mean, it's still under review, government stakeholder, and we probably can't release that yet. But we're working for someone to make a kind of an early warning detection system, situational awareness, which means provide them more context about it, and looking at forecasting symptom levels. So we're not doing an actual diagnostic piece, just looking at people, what they're talking about on Twitter, and relating that back to symptom outbreaks and things. I'll get into that in a little bit. So the first one we've talked about a little bit was Twitter influence, and this is most of this is from a paper called, a nice mouthful of a paper, ranking Twitter influence by combining network centrality and influence observables in an evolutionary model. So I guess I thought I'd start with some of the things. Why do people care about who's influential within a social network? So the main reason we were looking at that is within covert networks. So you may have a covert network which you could imagine might be partially observed as well. So you might be able to see certain people within this covert network, not see other nodes or people that are playing important roles, and you want to see what am I missing of this picture. So you can observe things through surveillance and certain things, but you can see that you might build up this network and there's something missing. So you're looking to see, is there an influence relationship that you haven't observed or something like that. That can tell you something about the network itself. Marketing and advertising, obviously people who are influential in social media are going to be a target for people promoting goods and services. So that's why it's important for marketing. organizational efficiency. So this is if you're looking at your company and trying to say, or a department or something like that, who is important within that. Again, like the point I made earlier about the between the centrality, who are the brokers that link departments. So that might be just to know who's influential might tell you that. Policing, so obviously influence policing could come from kind of riot situations or protests. We want to see the leaders of these ad hoc organisations that just come into being, and then how can you tell in a data-driven way who are actually the leaders of these things. So I think it's enough of that. So the model that we came up with then is called the reach buzz model. So the reach is basically centrality. So it's your ability to affect the network. So you've got this graph, and your position within it is your reach, your ability to affect it. So you can kind of substitute in whatever centrality measure you want. We use central. Yeah.
So is that measure just based on one node, or is it sister nodes? So the ones that it's connected to, if they're very influential, are you more influential?
Well, it depends which one you use. Yeah. So like degree is just based on you and those who are directly around you. PageRank is recursive. So it looks throughout the whole network. And for this one, we had 10,000 nodes about, and a couple of 100,000 edges. So we kind of closed off the network there. So it wasn't a complete PageRank, because when we sampled something from Twitter, had we actually followed PageRank through, it would just kept going, and the running time as well as the data collection, because you were rate limited by the API, would be difficult. So we kind of had a closed sample view of this network, but it is recursive, yeah. So it goes down and calculates that. Right. So then the buzz, and this is the one I'll probably talk about a little bit more, is we've got two concepts: your ability to affect the network, and then your actual observation of the effect that people are having on the network. So this is like people's stuff is getting retweeted, they're getting mentioned in tweets. People are interacting with them, they're talking with them. It's all these kind of observables that are not strictly topology, structure-based signs of influence. So people can be doing both, they can be doing one or the other. So you can imagine a very popular account with 10 million people following it on Twitter that doesn't tweet, isn't active. People just come and follow this person because they're popular in the real world. And so what we wanted is something that kind of unifies this approach or view of influence to take into account how active and how people are actually liking, endorsing and interacting with content that you produce to get a unified view of influence. So I guess at the related work there's some other works that I've kind of referred to here, but none of them, as far as I know, have unified those two. We've got some observation-based methods and some topology-based methods, and we've tried to combine them into one.
So, can I just pick you up on just the buzz? Do you have a time cut-off related to how long it takes for people to respond to a posting in determining buzz? Because we all know that there are very rapid peaks of attention and then it slowly decays through time, maybe through hours or days. So do you have a temporal cut-off, a standard one or a dynamically varying one?
That's a good question actually. I haven't been asked that one. I don't think because we arranged it all in a temporal way. If there was a retweet, no, actually, no, we don't. Is the first answer. I guess we haven't looked at somebody's post and then said when was that made and when did the reaction to it come. What we've done is we've got for everybody we've got a stream or time series across the way, and if that person that we're interested in, the potential influencer, has 5 retweets on that day, minute, whatever that time point is, then that's the information of the series at that time. We haven't tried to relate it back to the post that was made. It would have been actually difficult, not an impossible thing to do, and difficult and up to complexity a good bit to kind of relate that back. I guess you could have had a relationship to it, but we didn't actually do it. No.
Because buzz, in a sense, is a temporal density of responses, isn't it? So the shorter the time period, the denser the response rate. The longer the time period, the lower the density. And buzz is usually the higher density per time unit, isn't it?
Yeah, it is, and it's like one of the things that we did a survey of these users, and then one of the things that we see, and we've looked at individual posts before, is that you get a spike in the reaction and then it tails off, and within a week you've got nothing on it anymore. We didn't try and relate that for everyone, but hopefully the effect averages out that mostly at that time period the person that buzz is creating is close to that time period. I think that would be pretty true. But yeah, no, that's an interesting one. Yeah.
Thanks.
Okay, so do this one. So we used a hidden Markov model for capturing buzz. So those of you unfamiliar with hidden Markov model here. So what we've got here is we've got observations and the hidden states. So with the buzz, we've got these things that we can see about that people are doing or how they're endorsing people's content. We've got a retweet that says that you find this content interesting. We've got a mention, which is kind of attached to somebody's name or the value of that person's. It's to do with them rather than to the content specifically. The interactions are kind of a measure of engagement. How often are you interacting with people? And these things can be viewed as separate indicators of influence, or we can try and kind of combine them a little bit. So we've got combined them by taking these observations and then mapping them onto a kind of an abstract buzz state. So that we've just segmented it up into, that you're not creating any, which is the vast majority of people, but you're creating some a high amount of buzz and very high. And it's kind of hard to do that in, to give it exact ranges here because we're taking various different variables. And we want to do, from these observations that we've got, which is retweets, mentions, and unique interactions. And these are all counts. So this is like a discrete time hidden Markov model. It's not like a Gaussian or a mixture of that. They're all discrete variables. And we map these into different ranges and threshold them according to the data. So we look at the quantiles within the data, and we see what are really rare retweet counts, and just how rare they are, and from that process we get an idea of some of the thresholds for when a retweet count has gone into kind of a very high state, something like that, and we get those levels from the observation.
So, can just some detail. So, this observation is of particular user or particular tweet or a group, and what is the state space? So it's you said state, you quantize them, so variables. So how many variables? How big is the state space for chain?
So you've got, I think it was a 4x2x2. So you've got 16 entries in there, the symbols in the observations. There's categorical symbols, so just treat it as integers. Okay, so each value, say for a retweet, we might have low, medium, high, very high, because that was one of the most important. So we have 4 different levels of it. So with retweets, we've got 4 levels. Mentions, we've got 4 levels, and and the interactions only had 2. So then you get this 4x2x2. and then depending on your symbol, you get like 16 different integers, and that's all the HMM actually deals with. So we take these ideas of these observations and stuff and map them into kind of this Cartesian product symbol space, and that it can handle nice and easily. It's just got a string of between 1 and 16 as the integer input, and then you're producing out a state here.
But you question on what perspective? Is it a single user's tweet? Single person?
Yes, it is. It is the person that you're interested in. And I guess the goal of this is to see who's influential. So you look at all the users and you kind of do their influence. And at this point, we have a time series. I think it was over several months. And at each time point, you attach them one of these labels. And then in a later slide, I'll say how we go from this label to a kind of more numeric or quantitative version of actual buzz that they've created over a time, over a duration. But yeah, so that's how we work with this HMM, and then we give them a label set basically over your time period. So you have 6 months, and you're looking at every week. You've got however many weeks of these labels, and we've used the thing called the Viterbi path for hidden Markov models, which gives you the most likely sequence through the hidden states. It's not exact, and like these, when you're using these kind of things like none, some, and how you can't really be theoretically exact or whatever. You're trying to get to some sort of probable estimation of how influential somebody is. Okay. So yeah, so this is the part that I just alluded to there, is that we've got this series of states that somebody has, and then we want to say, like, how can I actually rank two people against each other? So we want it to be quantitative then. So we applied a simple transform to those states. If you're, excuse me, this is 0, 1, 2, 3, and if it's 0, you just leave it at that. Otherwise, you take the exponential of 1, 2, and 3. So we see that those people exhibiting things in the higher states are actually far more interesting than those in this some and none state. So as this reward, I guess, goes up exponentially, it kind of captures the relationship that these people who are producing retweet counts in for example, 70 retweets or something within this network is much more important than somebody rating 1 or 2. And it's much more likely an indicator of how influential they are. So that's why we have the exponential relationship in this reward. And that's what gives you the actual buzz of somebody over time. You apply this exponential reward at each time point over the series, and then so you get one single figure, because the buzz rank is the summation of all of those over your time period. Then how this is just the observable things that you can capture in a network, how people are interacting and using the content. This is when we combine it back with the information that centrality and the topology of the network gives you. So I guess the central premise at the start is that neither is both have their strength and both have their weaknesses. With there's a lot that topology is telling you, and we hope to add to it, I guess, by adding in this buzz measure.
And V of K is?
That is that's the reward. That's the Viterbi path, sorry. Okay, so yeah, I think that was the model and the approach we used. This image here shows, I guess, a snapshot of the network that we used to actually kind of evaluate all these things out. So this was, I don't know if any of you have heard of Scala, the programming language, but we took programming language centered around, we took a technical community on Twitter centered around the creator of this programming language, Martin Odersky. We took all of his followers and we developed a network from there. The benefit of this was that we knew that there'd be influential leaders within this, that there was at least some hope of finding it out rather than from kind of a random sampling. Also, we wanted to be able to compare this back to some sort of ground truth and a survey. So if we kind of captured a network and there was somebody that we knew, we were able to survey these people by just going directly to Martin and asking him to tweet a link to our survey. He broadcast it, and we got 150 respondents back. So we were able to kind of survey and direct the target network. That might be difficult to do in any other different, if you were to capture this network around certain keywords and then build that out, or if you were to capture it just purely from random sampling, might be difficult to get that ground truth. I'll come back to that. So that's why we went for this kind of seed-based sampling. I guess it was kind of slow with this network because there's Twitter APIs. So then, so this is the idea of why did we do this survey? So the survey was asking people to rank things in the list. We asked, I mentioned why we did it already, so that we get this ground truth and we can compare a list. A lot of the time with people having influenced the lists or things like that in the literature, all they do is compare, say, maybe retweets to your mentions and then look at the rank correlation and see what are the difference between the two. There's no kind of ground truth because it's difficult to assert. So we were trying to get as close to that as we can, even if it's difficult because you're only sampling from, 150 people. It's a small enough sample of that it might not tell you everything, but we hoped that it was going to be more informative than just comparing it to another influence type list. One of the things we did find with this survey is that people found ranking 10 people a little bit too difficult cognitively. So half of them didn't do it. Half of them got to the page and said they were going to do it, and realised it was too much work. So I don't think that was too surprising for us. We couldn't have made it much easier, but we needed to have a rank, and I guess maybe we could have done 3 or 5 or something like that. We were already kind of putting ourselves down to look at just 10 users. Maybe 10 was too large, I'm not sure. It was an interesting thing there on kind of perceived cognitive effort. Half of them didn't even attempt it once they was involved. So yeah, the results for the survey, the full results are in the paper that I provide as a reference. So it's just, I guess it's interesting to see that this is the method that we use. It got about 6 people that were in the survey in the same top 10, and it improved on their page rank on its own, brought another 2 people that went in there into the top 10. So you see here that this buzz, which was kind of an abstract label before, is now actually just this count that we have, and this is when we've applied that reward to it at each of the time points and then summed up those. We've now actually got a number here in this page rank, centrality. Simple combination function is just multiply the 2 of them, and then we see we can re-rank based on this reach and buzz. So not always too happy with the terms, but the idea that they're trying to convey is, that this is what you can affect within the network is the reach, and the buzz is those things that isn't studied too much, is that you're actually affecting, and then we can see that you're doing that. Right. So I think that's the end of the influence stuff. Oh no, actually one more. Yeah. So we had this ranked list of influencers, and that was one of the outputs. And the next one was trying to actually predict forward buzz states. And this is not too well labelled, but these are the 4 states we looked at. This is none, some, high, very high. And then this is the comparison of these this model that we have, which is the buzz model, against other naive models. So we've got just one that's drawn from a similar distribution, which is a negative binomial. We've got one that's just purely one all the time, which is just like a no information classifier. You're just predicting the most frequent thing in the data set all the way across. And then there's just a uniform distribution. So we didn't really have any other comparative technique to use against them, so we just used these control models. What we're trying to do with the HMM when you're trying to predict forward is you don't have the future emissions, you only have the transition. So you're in a state, I'm in a state, say, I'm very high today, very high buzz exhibiting today, what am I going to do tomorrow? And that's so it's only after the transition model. What am I likely to be in tomorrow? So if that has a very high transition, that you stay in that state, then you might be in that state going forward. So that's how you predict forward with the HMM. We've only got the transition model, because the HMM is essentially composed of a transition and emission model. Right. So the results we found was like it was good, very good 1 week out. Not so getting worse, but okay up to about 3 weeks, and then it just deteriorates. But maybe that's okay if you're trying to say, if you're advertising or something, who's going to be what's going to create a buzz next week or something like that. Our kind of view is that we won't. The fact that it's short term, it could still be okay. It depends, I guess, on your application. If you're looking for long-term prediction into the future of this really kind of ephemeral concept anyway, it's short-lived ideas, buzz, like you say, with a short time density anyway, so it's hard to predict into the future. Okay, so I guess that's it for the influence work, and I'm not sure, like, it's a little bit difficult for me to gauge the level of people in the audience here, so I might be going really high level on something and skipping past other things. But I would guess it just keep on. So yeah, this is the last piece of work is focused on the network and looking at the connections people have between each other. This one, although we used a little bit of it, we ended up throwing it away. So it's almost completely just about posts and the tweets that people write. But it's still been really useful. What we're looking at here is there's a name to this project which I can't give, which is probably what it does though is we're looking at early warning detection of symptomatic events. So people tweeting things like, I have a terrible cough, and my eyes are itching. I've got such bad flu, things like this. And you can imagine how over the country, we looked at England and Wales, that you can see spikes and peaks in behaviour when people are actually, if there's a flu epidemic or there's the flu season has started, you might see how counts of tweets mentioning flu, cough, influenza, things like that will start to go up and form a peak. You've got problems of noise, like a word like fever, it could be Bieber fever or night fever. There's other uses of language. So you've got lots of noise in the Twitter data, but it has got high coverage. It's, in the UK at least, there's a lot of tweets to work with. So it's a good signal that can tell you something before GP visits or something like that will, because they have a lag. Somebody has to exhibit the symptom and then go to the hospital. That needs to be reported and produced and sent out, as a report. So there's a lag inherent in those things that you don't get in social media, whereas in social media the problem that you have is how do you know that this thing is actually real? It's like there's noise, there's various different types of noise. So that gives you an idea of how you might have early warning detection. You see this big spike in activity, and you're like, right, is this an alarm or an alert? Is this something you need to be concerned about? Situational awareness is like, now that I've seen that this thing is an alarm, alert that I'm interested in, tell me something more about it, automatically summarize it for me. And then forecasting is a little bit more obvious. So people have heard of Google flu, where you're typing in search terms, and people are talking about cough medicine and stuff, and then they relate that then back through some regression model to being able to predict the flu season, because people are typing these things in their search terms. So we did some forecasting as well on 4 diseases. Right, so we used 3 sources. We had Twitter data, news articles, and clinical data. We've used them for different reasons. Twitter data is like the primary source of information. You're looking at counts. It's fast. It's pretty much real time. It's high coverage. It's got a lot of the country covered. You might have slight demographic issues about younger users and things like that. It's more biased towards urban than rural, but it's going to give you pretty good coverage. The problems with it are it's noisy, the language is poor, there's problems with the structure and things within the language. If you want to do things that are classic in natural language processing, that come from books, articles on the web, you have to kind of sometimes just reinvent them or do them differently because people don't speak the same way in social media or on Twitter. But what the strength of it should outweigh the weaknesses for our situation, because we generally want this to be an early warning detection, which means you need to detect it before it's in the news or it's in the GP data. We use the news to kind of confirm something after the fact. So it's like it can, once we've seen this event and you've extracted it automatically, can we find maybe some days later or some time later some news articles that kind of support that as being an event and give you more information. So that's maybe the situation where we're in this part, that it can link tweets to news automatically. And we've just finished doing that. It's worked quite well. And then, so this clinical data is the last source, and the reason we use that is not actually to go into the pipeline of getting you early warning events, but to say, to evaluate. You've got an early warning detection algorithm that says this is an event, you could just make that up unless you've got some sort of evaluation. So if it's a symptomatic one, we have to compare that to GP visit data and see after we've said there was a spike, is there something that showed up in the GP data that would confirm or deny that? And I guess the rest of this architecture diagram just goes into how we process the tweets, pull them in, put them into a warehouse, and then able to query them and things. It's not so important. The first thing we did in this project, or one of the first things, is we wanted to have location, because we wanted to see where these outbreaks were happening. It's kind of important with this early warning detection. If there's an outbreak of norovirus in Sheffield or something, you don't need to report or flag it for the whole country. It's kind of important where that is. So we could have gone at the county level, county, city, and all these administrative regions within the UK, but we did it slightly differently. We wanted this data-driven approach to giving you areas or clusters within the UK that we're concerned about. So on the left here we've got this map, which is the UK population density. In the middle we've got a sample from our tweets. We've got this streaming API, which is connecting tweets from a boundary box around England and Wales. And so from Scotland and Northern Ireland, we haven't actually used them in the study. But, it's just connecting tweets, and then we draw it up, and we see this kind of formation when you just draw all the geotagged tweets, so that each one of them has a coordinate. Then we're like, okay, we can kind of see some patches here, and let's try and extract out some actual clusters or areas that we can work with at kind of a coarse grain to see outbreaks and things like that. So we ran a clustering algorithm, density-based one, dbScan, on that data, and this gives us these clusters that we can use, and we can then label them, and this actually forms a network for us. And I think apart from like this Manchester and Liverpool kind of conglomeration, everything else is pretty nicely separated. And I think that might be Newcastle and Sunderland as well. But that's kind of how DB scan works. So you kind of need gaps between things, and when there isn't that gap, you just become one area. But it works pretty well for what we want to. We want to be able to detect when something is an outbreak here or here, and maybe how likely it is to spread to neighbours and things like that. So this kind of coarse view of those areas is fine, and it's from the data. So you can apply this to a different country with exactly the same method. So, yeah. One of the first problems is with noisy data. So I can't remember. I think the orange ones here are things that match our keywords but are nothing to do with I don't know. Oh, so hemorrhaging. Right, yeah. So yeah, the orange ones are matching our keywords. So we started off with a symptom keyword list, and we got this from Freebase, which was useful because we didn't have to come up with it. We just downloaded everything from Freebase that had the tag symptom on it, and then we did this. We sort of looked for what was actually in our tweet database and filtered a lot of those symptoms out because people don't talk about them, medical language. So that was kind of how we started with our keywords, and then you have these problems that people are mentioning these keywords in different contexts. So let's not make rash statements. So rash is a particularly noisy one. It's just speed up a little bit. So I think you get the idea there. So then what do we do to solve that? So we've got health document classifiers. We've got one for tweets and one for news. The one for news is quite basic. It's just a naive-based classifier. You give it some news or some health sources, and you give it some non-health sources, and it works accurately enough. The Twitter one is a little bit more difficult, but we didn't have to reinvent this, so we took the model from Adam Sadek. So it's a semi-supervised vector machine. Semi-supervised means you start with a small training corpus or training set. We had like 5,000 tweets that we had to manually label ourselves. Then you expand that. So this is where it's semi-automated process. So you expand from 5,000 to those that you definitely know are sick, and those that you definitely know aren't. And then they give you another expanded set. From that expanded set, you then create a final training set of high likelihood ones. So you get from your 5,000 to 1,000,000 training examples from the semi-supervised approach, and then you're able to actually just run your linear kernel SVM on this million training examples, and it works pretty well. You got like 96% accuracy on a held out set of tweets. And that's pretty good because there's a lot of these keywords when you're looking at that are going to be mentioning things that are nothing to do with health. So then, yeah, I realise now for a 3 o'clock finish I'm going to have to zip through some of these things. So, yeah, early warning detection. Basically, once we've got those, the noise out of accounts, then you have just imagine a time series. So all these tweets have just been reduced to time series accounts about symptoms. We're not trying to do any diagnostic elements, so we said that if there's a flu, or sorry, if there's cough outbreaks or things like that, we're not doing the diagnostic piece just yet. So it's interesting for an epidemiology researcher to see this outbreak or alarm to do with cough or something like that. And later on you can use that. We do comparison to clinical data. This is how we evaluate the method and see that it works. So if we were recording people saying hay fever and there's big spikes in hay fever, we go to the Public Health England's website and we refer that back to their entry for allergic rhinitis, and you can see that they give it kind of a trend, whether it's no trend, increasing, decreasing, and you can compare your own data with alarms back to this graph. You can see have you actually got an event that you should be concerned about.
Why can't I see a lag between the two curves?
Sorry, this is just, I haven't I've only put the allergic rhinitis one
Oh,
up there.
right,
I haven't put the two up there.
Right,
I think I do to that. I trimmed that slide out. Oh no. Does that have it? No, exactly. Okay. So you've detected an event and then you want some more context around it. We've looked at the, how do I get the really quick version of this? You've got an alarm or an event, it's got maybe 500 tweets in it, people are talking about something. Say it's this asthma in London. A few months back, there was the Sahara dust cloud. So we're trying to extract out the cause of an event or spike. So you've got maybe 500 tweets that people are talking about this asthma, smog, Sahara thing that happened in London in April, I think. And then you have maybe the past month tweets, 1,000 or 2,000 tweets. You're not talking about Sahara, you're not talking about the smog, but it's a baseline, it's a representative baseline. They're talking about asthma and things like that, and their chest feeling sore, but we can extract out, because they're statistically different in this Fisher's test that we use, terms like smog and Sahara out of that, and you can kind of extract the cause out of an event from that method. So seeing as a statistically different frequency of occurrence for these terms. And this kind of gives us some idea of what has caused an event to happen. So from that, we can then go search the news, and use Sahara dust as a news term because you've extracted it out, or smog in April, and that'll get you some news results. We can see how good that news is. Are they all related to each other? If they're related to each other, then we might attach the news articles to the tweets as an event summary. So that's, I guess, what situational awareness does. This is a screen that we did for this project. This is one particular event, I think it's the asthma one. So we just see here's the time series spike in the initial mentions around asthma and all the other keywords that we're tracking for it. This spike triggers the alarm in the kind of biosurveillance detection algorithm. We then, because of that, go and fetch some extra information. We can view the tweets because they're all on ToCAI. We can view them on the map. We can extract out word clouds. We can look at clusters and hashtags that people mentioned. And we can link in articles for news as well. Because we know automatically we've got some about the important terms. The network effect there.
3 o'clock teaching effect.
Sorry?
The 3 o'clock teaching effect.
Okay, it's okay.
Press the button at the left of the door. That's the one.
Sorry, now, I thought I'd actually go probably quicker to the first bit. Should have.
It's okay, come on.
Okay, so we've got this. The last thing that we did is the forecasting, tracking. This is where we're trying to, like Google Flu, we have sources of information which are the tweet counts, and we're trying to match them up or to predict ahead maybe next week of your GP visit. So you have a time series which is your GP visits. We're trying to say what's the value for next week going to be. What we've got to tell you that is, I guess it's forecasting, sorry. Let me just explain the core of this one right. You have last week's GP visit figure at this week, and you have all your tweet count information. You don't have this week's GP figure because it's lagged by 1 week. This week's GP figure doesn't come out until next week. So you're trying to predict this week's GP visit figure using today's tweet count data and last week's GP data. So that's the problem that we found ourselves here. Basically, it's similar to that Google Flu Trends. It's a regression problem. We've got